We will continue with our study of the derivation of the equation for non-isothermal systems. This we have started in the last class, and we have proceeded by defining a control volume of dimensions del x, del y, del z, and we have identified through each of the 6 faces, that is at face at x and at x plus del x, y and y plus del y, z and del plus del z, some amount of energy comes into this defined volume by means of convection and by means of conduction. So, whenever there is convective flow into the volume element that we have defined, that flow carries with it some amount of internal and kinetic energy, and it is going to come at x and it is going to leave at x plus del x. So, we have identified 3 pairs of terms, one showing the amount of energy both kinetic and internal that comes in at some phase and leaving at x plus del x, leaving at y plus del y and leaving at z plus del z. So, these 6 terms together would give us the total amount of energy that is being added to the volume element due to convection. Similarly, we have also identified the conductive energy which flows into the defined volume element because of a difference in temperature. So, there is no velocities involved since conduction does not require any movement of the medium. So, we have expressed the heat flux at each of these locations such as Qx, Qy, Qz, those 3 are the in terms, that is the flux, and the one that goes out at x plus del x is simply denoted by Qx plus dx, Qy plus dy and Qz plus dz. So, the net amount of energy, thermal energy, which is being added to the defined control volume, the volume element that we have defined, should be, if we just consider the x phase, the amount of energy that comes in per unit time would be Qx, which is the flux, multiplied by the area, and the area of the x phase is simply del y times del z. So, the amount of energy, thermal energy, that is internal energy that is being added to the volume element would simply be Qx evaluated at x multiplied by del y del z, and the going out term it would be minus of Q x plus dx, that is Qx evaluated at location x plus dx multiplied by the area, which remains the same, that is it would be equal to del y del z. So, these 2 terms would give us the conductive energy which is being added to the volume element through the phase at x and x plus del x. Similarly, I should be able to write what is the energy being added through y and y plus del y and z plus delta z. So, the algebraic sum of these 6 terms would give us the total amount of internal energy which is being added by conduction to the volume element. So, I have 6 terms for convective flow of energy and 6 terms for conductive flow of energy. That together would give me the total amount of energy being added to the system. In this system, we have to identify that it is an open system such that the fluid is allowed to enter and leave to the volume element. So, that gives us the total amount of energy being added to the system. And if we think about the first law of thermodynamics, we would also have to take into account the work done by the system or work done on the system. Work done by the system is going to result in a reduction of its energy. So, it would come with a minus sign in front of it, and work being done on the system, since it increases the energy of the system, so it is going to come as plus with a plus sign. And the work done can be against different forces. The forces can be categorized into 2 distinct groups. One is a volumetric force, the force which is acting on every point inside the volume element. So, a common example of that would be gravity, and it could also be done against surface forces, and one of the surface forces which we can easily identify is the pressure. So, when we talk about the work done against volumetric forces or against surface forces, the work done would be simply force times distance and the rate of work done would therefore be force times distance by time, and since distance by time is velocity, so the rate of work done against or by external forces, be volumetric or be it surface forces, would simply be the force multiplied by the velocity in that direction. So, when we talk about the force being exerted due to pressure on the x face, would simply be P at x, pressure evaluated at x, multiplied by the area of the x face being del y del z. So, this is the force P at x multiplied by del y del z, this is the force, and it has to be multiplied by the component of velocity in the x direction, which is Vx evaluated at x. So, the entire work done against pressure forces would simply be Px evaluated at x multiplied by del y del z multiplied by the component of velocity, which is Vx, also evaluated at x. And the work done on the other side at x plus delta x would still be the same, except the pressure is now evaluated at P at x plus del x and the velocity is evaluated at x plus del x. In a similar fashion, I should be able to find out what are the other 4 terms. For example, the y term would be Py multiplied by the area of the y face, which is del x del z, multiplied by the component of velocity in the y direction, which is Vy, and the one that's on the y plus del y face should simply be Py at y plus del y multiplied by del x del z multiplied by Vy evaluated at y plus del y. So, these 6 terms together will give us the force, the work done against the surface forces. Similarly, I have shown is in last class the expression for the work done against volumetric forces. I have purposefully omitted the viscous dissipation term, that is the force, that is the work to be done against viscous forces. As I have said, the viscous forces, the viscous dissipation or the work done against viscous forces, they become prominent as compared to the other terms under some specialized conditions. The specialized conditions generally refer to if the viscosity is large or if the velocity gradient is large. So, the velocity has to be large and the length scale over which the velocity changes is small, such that del Vx del y, if that is the velocity gradient we are talking about, this has to be large and mu has to be large, the viscosity has to be large. So, if those 2 conditions are satisfied, then the viscous work done against viscous forces, which generally is manifested by a change in temperature, since it is a dissipation function, it is going to give rise to a change in temperature, give rise to energy released, and therefore, the temperature will also change, and this term which takes into account the work done against viscous forces would only be important in 2 or 3 cases, as I have mentioned. It could be for re-entry of a rocket or for very high viscous fluid when it is flowing through a small conduit, a thin conduit, such that the velocity may not be high, but the distance over which the velocity changes is very small, which would be relevant in an upcoming area of fluid mechanics, heat transfer and application, which is known as microfluidics, where the structure of the system in which this change in velocity is occurring is very small. They are of the order of tens of microns or maybe hundreds of microns. So, even though the velocity is small, since the length scale over which the velocity changes is of the order of microns, the velocity gradient itself is large. So, in some very high speed extrusion of polymers, re-entry of rockets, or in some microfluidic systems, this viscous dissipation can lead to significant changes in energy, and those terms must be included in the energy equation. But I would not derive those terms, but I will show you from the textbook what would the energy equation look like, and you can easily identify the terms which correspond to viscous dissipation that we are not considering at this point of time. So, the result of all these heat input, all these energy coming in by convection and conduction, and the energy change as a result of work done by the system against volumetric forces or against surface forces, when you combine all of them together, and if the system is at unsteady condition, if the system is not at steady state, then the algebraic sum of all these terms should result in a change of the net energy content of the defined volume element. So, the change in energy content, both internal energy and kinetic energy of a volume element in an open system, is a result of several factors: the conductive flow of energy, the convective flow of energy, and all terms that refer to work done by or on the system. So, this much we have covered in the last class, and when you see this equation, the one that I have shown over here is what I have described. The rate of accumulation of internal and kinetic energy is equal to the rate of internal and kinetic energy in by convection, out by convection, and the net rate of heat addition by conduction, and the net rate of work done by the system on the surrounding. And since it is by the system, that is why it comes with it is preceded by a negative sign. So, which is nothing but a first law of thermodynamics for an open system. So, after that what I have done is I have defined the volume element in here as this is the volume element, and I have identified what are the terms for convection. I have also identified what is the energy input by conduction. So, these are the 6 terms that I have referred to, and then I have also identified the work done against volumetric forces, for example, against gravity and against pressure, which would be these terms. So, when I combine all these terms together and divide both sides by del x, del y, del z, and then take the limit when all of them approach 0, what I get is a reduced form of the equation, and I am going to write the final form of the equation as rho c d temperature by d time is equal to k del square T divergence of T minus T of del P del T times velocity, this is velocity, plus mu phi v. I have omitted a large number of steps in between, which would be available in your textbook. So, I am not going through all the steps in the class. What I would like to do is I like to clarify the genesis of each of these terms as I have described as a result of conduction, convection, work done, and unsteady state effects. So, what you get out of that is the energy equation. Now, from that generalized energy equation, I subtract the mechanical energy equation, and what I get is known as the heat transfer equation, the energy equation, where only internal energies are taken into account. So, if you look at the terms over here, the first term, this is the unsteady term. This d dt has a special meaning. This d dt, the capital D dt, this capital D of dt, it is known as substantial derivative. This is a special mathematical function which simply tells you this is going to be equals del temperature by del time plus Vx del temperature by del x plus Vy del temperature by del y plus Vz del temperature by del z. So, this is the expanded form of the d dt, this one substantial derivative, which is defined in this way. So here if you see, this term is definitely the unsteady term. What about these terms Vx, Vy, Vz, and with a temperature gradient in there? So whenever you have velocity associated with any term in energy equation, that should refer to convective flow of heat, because only in convection you have the velocity associated. So convection takes place only when the medium has a velocity of its own. So if you concentrate on, if you look at the first term on the left hand side, the first part of that del T of temperature, that is the unsteady term. The other three terms all contain the components of velocity, which are Vx, Vy, and Vz in a rectilinear coordinate system. So since they have velocity in that in its form, so these three terms refer to the convective heat transfer process. So therefore this whole term is unsteady plus convection, where this term is due to the unsteady behavior of the system and the convection is represented by these three terms. Now what is the first term over here? I will call it as second, and this is the third term. The first term on the right hand side, if I concentrate on the first term on the right hand side, it is going to be k del 2 t del x square plus del 2 t del z y square plus del 2 t by del z square. And you can clearly see what is the significance of this term. They have the K, the thermal conductivity, and they talk about temperature gradient. So K del 2 t del x square is nothing but the gradient in the heat flux, because you can write K del 2 t del x square as K times del x of del t del x, and you can bring this K in here. So this becomes del x of K del t del x, and if I put a minus sign over here and a minus sign to balance the minus that I have introduced here, it is going to be minus del q x by del x, since by Fourier's law minus k del t del x is equal to q x. So this term gives me the del x of the q x, the scalar component of the heat flux vector in the x direction. Similarly, del 2 t del y square would simply be minus del q y by del y, and this term would be minus del q z by del z. Okay. So these three terms on the right hand side, which I denoted by 1, is nothing but it represents the conduction heat transfer or conduction energy transfer. So the left hand side is unsteady and convective heat transfer. The first term on the right hand side is conduction heat transfer, as I have shown here. The second term, the term 2, is due to expansion effects. And if this is expansion effects, it essentially tells you that what would be the effect of this expansion effect, what would be the work done against pressure forces and so on. And the third term, which is mu times phi v, this is known as the work done against the surface forces, which is the frictional effects. This is known as the dissipation, and this dissipation is due to friction. this phi v is known as the dissipation function, and the form of this phi v is quite complicated and I did not derive it. So, therefore, the equation, the energy equation, the complete form of the energy equation, I did not derive all the terms, but what I have done is I have shown you the significance of each of these terms in the overall scheme of things. So, for most of the practical cases, this third term can be neglected. The phi v, the dissipation function or the energy change of a system due to viscous dissipation is neglected, and you can clearly identify, easily identify the term by noting that you have a mu in front of this. So, all the terms which have the viscosity in front of them in the energy equation, they refer to the dissipation function, and therefore, for most of the practical situations this third term can be neglected. The second term may or may not be relevant. So, the second term will have different connotation in terms of its significance in the energy equation, and let us see what when it would be relevant and when it is not relevant, and we can get back to an equation that we are more familiar with. So, I am writing this equation once again. It is rho c, c is the heat capacity, the substantial derivative of temperature, which is equal to k times del square T, which is the conductive heat transfer, T times del P by del T times divergence of the velocity vector plus mu phi v that I am setting equal to 0 for our case. Now, if it is a for fluids with constant pressure, which is a reasonable assumption in many situations, or if the rho, the density is a constant, then if fluid is with constant pressure, then this part is going to be 0, and if rho is a constant, then this part is going to be 0. So, if rho is a constant, then del V would be equal to 0, which is nothing but one form of equation of continuity that you must have studied in fluid mechanics. So, if rho is a constant, this part would be 0. If fluid is at a constant pressure, then this term would be 0, and this is anyway to be equal to 0. If we use any of these conditions, then the equation would be, this is the form of the equation, energy equation, which is mostly used for convection as well as conduction. Now, let us see what is going to happen if it's a if it's a convection plus conduction, both are present. I expand this term, which would be del temperature by del time plus Vx, del T by del x plus Vy, del T by del y plus Vz, del T by del z, which is nothing but the expanded form of this substantial derivative, as I have described before, would be k by rho c, I have brought the rho c on this side, times del 2t del x square plus del 2t del y square, and for the z. If this is the case, and if it is a conduction only case, so if this is a conduction and convection both are present, then this would be the form for a rectilinear coordinate system if it is a conduction only case. Now, what is going to be the conduction only case? What is this? What are the simplifications that I can make? This Vx, Vy and Vz are going to be 0, since in conduction you do not have any velocity of the medium. So, since in conduction you do not have any velocity of the medium, velocity of the fluid itself, then Vx, Vy and Vz all are set equal to 0, and therefore, this equation becomes del T by del 1 is equal to K by rho Cp or C times del 2 T del x square plus del 2 T del y square plus del 2 T del z square. So, I think you can recognize this equation now. This is the equation which is also known as the heat diffusion equation that we have studied before. Heat diffusion equation that we have studied before. So, I will write it once again. The heat diffusion equation one of the things one should always do is, whenever you develop a new equation, you should always try to see if it reverts to the known form for limiting cases. So, the equation that we have derived is a general equation, is energy equation, where we have taken into account the unsteady effect. We have taken the effect, we have considered the effect of convection, conduction, work done, and viscous dissipation that we are not considering. So, to this equation, now I am going to impose the condition that there is no expansion effects or the density is constant. So, I take care of the second term on the right hand side. So, I am left with one term on the left hand side and one term on the right hand side. The term on the left hand side is the unsteady state effect and convection together. The term on the right hand side is only the conduction term. What I have done after that is, I set convection to be equal to 0 by setting the velocities to be equal to 0, the velocity components to be equal to 0, and therefore, what I have is the heat transfer due to pure conduction. So, heat transfer by pure conduction we have seen before, we have derived before in conduction, which is the heat diffusion equation. So, in the limiting case of no convection and no work done, what we get is the heat diffusion equation. So, if you see this equation once again, if this is for a one dimensional conduction only situation, let us say the temperature is a function of x only, it is not a function of y or z, then this equation would be K by rho Cp times del 2 T by del x square. So, this would be the equation for this, and if I simplify it further, it is one dimensional conduction only situation, but at steady state. So, if it is a steady state case, then this temperature is a function only of x, it is not a function of time. So, what you have then is K by rho Cp times d2 T dx square to be equal to 0. It is a temperature is a function of x only, it is not a function of x, and temperature is also a function of time in this case. Here temperature is a function of x only. So, this can be cancelled, and what I have then is d2 T dx square is equal to 0. So, this must look very familiar to you now, since you have studied conduction. If you have heat generation due to some electrical sources, heat generation in the system, then you are going to have plus q dot by k to be equal to 0. So, this form of the equation you have seen before. So, which is the one dimensional conduction only steady state situation with heat generation, and if you set heat generation to be equal to 0, this is what you are going to get, and where you should the solution of this would be T is a linear function of x. So, you can clearly see that starting with the most general and slightly complicated expression, you can see this is the expression for where you have conduction, you have convection and conduction both present, which is this form. If you set the convection to be equal to 0, what you get is the heat diffusion equation. If you simplify the heat diffusion equation by assuming it is a one dimensional conduction only case, you get the equation which is the equation for transient one dimensional conduction. So, this is the case of transient one dimensional conduction case, and when you drop the transient, make it a steady state, you simply get this d2t dx square is equal to 0. No need to use a partial differential since temperature is a function of x only. So, T is a linear function of x, and if it is a system with heat generation, you simply add the heat generation term where q dot is the energy generated in the system per unit volume. So, with this, that concludes the development of the heat diffusion equation in our for most of the cases. And if you look at your textbook in Cropera and DeWitt or any textbook will have this energy equation in I have discussed the Cartesian coordinate equation. You would see that in cylindrical coordinates and you would see that in spherical coordinates as well. So, the trick is to first identify whether you have a cylindrical system or a Cartesian system or a spherical system. Then look at the equation, look at the full form of the energy equation, and then depending on the situation at hand, cancel the terms which are not relevant. So, if it is a conduction only case, cancel all terms which contain the velocity, velocity in its velocity. If it is a steady state case, cancel the term which has the temperature derivative of time derivative of temperature. If it is a situation in which viscous dissipation is not relevant, drop all terms that contain the viscosity mu. So, I will just show you an example which is the full form of the energy equation in Cartesian and in cylindrical and so systems. So, this is the equation that you would see, and it is available in your textbook. So, if you look at carefully over here, this is rho Cp. I do not know if you can see it properly. I will read it for you so that it becomes clear to you. Rho Cp del temperature by del time plus Vx times del T del x, Vy times del T del y, Vz times del T del z. So, you have a transient term and 3 terms which contain velocity. So, they must refer to convection. As I have shown you, the entire left hand side is a combination of transient effects and convective effects. When you come to the right hand side, you have k del 2t del x square, del 2t del y square and del 2t del z square. This term contains k the thermal conductivity, and I have shown you that these 3 terms refer to conductive heat, the heat transfer due to conduction only. And finally, there is a complex set of terms which are nothing but the gradient square del Vx del x square, del Vy del y square and so on. But the important point to note here is that all these terms, they contain mu explicitly. So, since they contain mu, without even knowing the full derivation, you know that these terms that contain mu refer to viscous dissipation, the dissipation of energy due to viscosity of the solid. And as I said, it becomes relevant only for high speed, high viscosity flow or flow in small microfluidic systems. So, for most of the practical purposes, you do not need to consider these terms at all. You are going to concentrate only on the left hand side and on the right hand side, the right hand side for convection, the left hand side for transient and for convection. So, that is the governing equation which we are going to use for all our treatment of convection subsequently. Similar to the rectangular coordinates, we have the equation in cylindrical coordinates as well as in spherical coordinates. The significance remains the same. The left hand side contains a transient term, n terms which contains Vr, V theta, Vz. So, they must refer to convection. The right hand side there would be 3 terms, these 3 terms which contain K. So, they refer to the conductive transport of energy. All the other terms that you see contain mu. So, this entire group of terms, they refer to viscous dissipation in cylindrical systems that can be neglected in most of the applications. And when you come to spherical coordinates, again the same thing: transient, convection, 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 conduction, 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 and the rest of the terms contain mu. So, this entire set of terms is nothing but the viscous dissipation which can be neglected. So, what we have seen in this class is the derivation, the simplified derivation of the energy equation, where all effects are considered. The energy equation that we have derived starts from a very fundamental law, which is the first law of thermodynamics for an open system. We have taken care of convection, conduction, the work effects and everything else. So, this would be the starting point for our studies in convection. So, this is a slightly complicated concept, but I think once you go through your textbook and read look at the equations carefully, I am sure the concepts would be clear to you, and if there are any questions, I will be more than glad to answer them. And once you master these equations, at least the significance of the equations, then the rest can move in a much smoother fashion.